Evaluating the performance of forecasting models is frequently challenging. Computer software gives us the opportunity to make numerous forecasts to handle large volumes of data, but then the challenge is how do we evaluate the results? This section will present a couple of measures of forecast accuracy, but whenever possible, it's nice to take a look at a forecast and use the human eye to make judgments. For example, if we look at this data and the forecast in the green line, in the beginning, it looks like we have the correct model with the data. It looks like there's no pattern, so a smoothing model that manages to be in the middle of the data is an appropriate choice. However, there appears in period 8 and beyond for a trend to develop, and our forecast is constantly lagging it. We would want to get a trend model that would actually get in the middle of this data and forecast a trend into the future. One of the things we'll look at is how do we detect this shift from a model that works to a model that doesn't work. We'll look at a method to look at that, as well as methods of measuring forecast accuracy. Again, when we look at forecasting, we need enough data to initialize the model. For monthly data with seasonality, we would want 24 data points to initialize the model. We don't do evaluation in this period because it's basically taking an exam knowing most of the answer key. We're taking a model and fitting data points knowing the answer. So it is important to look at this to make sure that we have the correct model that it seems to match, but the accuracy in the initialization period would be higher than we would expect using the model to forecast. The ex post forecast region, if we have additional data beyond what we need to initialize, is where we evaluate forecasts, where we can compare the forecast data to the actual data and see how accurate our forecasts are. Then we make a forecast in the future where we have no idea what will happen, except that we know our forecast is going to be wrong, but hopefully it's going to be close enough that we plan well enough to be successful. When we look at measuring forecast accuracy, we measure errors between the actual data point and our forecast value. So we're looking at the vertical distances between the data points and our forecast line. It takes 2 years or 24 months of data to initialize a model. This is the extra 12 months of data where we can do the ex post forecast evaluation. So we set up a table, we look at the forecast value and the actual value, and in this case we'll define our error as forecast minus actual. Some textbooks and some software might identify it as actual minus forecast. Doing the forecast minus actual says that a positive error means that we over forecast and a negative error is an under forecast. So this method of comparing forecast to actual versus actual to forecast typically is more intuitive. But again, you need to check your software to see which way it's being calculated. One error measure we can look at is simply calculating the difference between forecast and actual and totaling them up. Another method is based on taking the difference between forecast and actual and using the absolute value function, in essence declaring all negative values to be positive and totaling those up as well. So we have two sums. One is just the errors, leaving the positive and negative values to cancel each other out, and one making an absolute value function of those differences, making all those values positive and totaling those up. This is the same table. We've just removed some of the data in the middle so that we can fit some calculations on the page. If we take that sum of forecast minus actual, not taking the absolute value but just totaling that up, we take that total, divide by the number of comparisons we have, which is 12, we will get an error measure called the bias. Again, if we're in the middle of the data, the positive and negative errors should balance each other out. That should be getting close to zero. If we have a positive value or a negative value that's significant, then we figure that we have a bias in our forecast, a tendency to under or over forecast. Here, the bias is minus 1.08, which means on average we're under forecasting by 1.08 units. So it's not a significant bias at this point, but we are slightly under forecasting. The mean absolute deviation is calculated using the total sum of the absolute value of the forecast minus actual, again dividing by the 12 comparisons that we have, and we get a value of 30.42. What this says is, on average, the forecast compared to the actual is off by 30. Sometimes it's off in a positive direction, sometimes a negative, but the average forecast is within 30 plus or minus the value. Half the forecasts are farther away from the actual value by 30, whether positive or negative. Again, the bias looks at the tendency to over or under forecast. The MAD gives an average error, ignoring the direction. Errors are always bad, so we would like to have a value that is close to zero as possible. Also, the error measures look at the ex post forecast region. How well the forecast will work in the future is still uncertain, but it gives us some ideas to how well our forecast model is working with the data that we have. The measures that we presented, the bias and the MAD, are absolute measures. We're going to look at the need for relative measures here in a second. To provide some background, let's look at forecasts for two sets of data, and let's look at the error measures. For data set 1, the bias is 18 approximately, the MAD is near 44. For data set 2, the bias is 182 and the MAD is 912. Just looking at those two comparisons, we would think that data set 1 has a more accurate forecast, but if we look at graphs of the data, there's data set 1, there's data set 2, it actually looks like data set 1 is not as good as data set 2. It certainly doesn't look like data set 2 is much worse, and it's probably better. What explains this is that the size of the numbers we're forecasting in data set 1 are under 1,000, whereas in data set 2, our numbers are almost to 30,000. So we're forecasting larger numbers in data set 2, therefore the errors are going to be larger in absolute value. But on a percentage basis, they're not as large. And so while the errors would be significant and large, and financially may be large, when we're evaluating forecasts and how accurate we would expect them to be, we really want to think on a percentage basis. Are we within 2, 3, 5%, or are we off by 20 or 30%? If we have a large number of data sets where the size of the numbers vary significantly, it's difficult using the absolute performance measures to tell when we're doing a good job and when we're not doing a good job. Therefore, we're going to look at the mean percentage error and the mean absolute percentage error as relative forms of the bias and the MAD that allow us to compare forecasts for different sets of data. The mean percentage error is basically the same formula as the bias. We're summing up the differences between the forecast and the actual, except in each case we're dividing by the actual data value. So we get a fraction, basically the concept of a percent, and then we take an average of that. Similarly, the mean absolute percentage error is taking the same sum of the absolute values of the forecast minus the actual, making all differences positive, but again we're going to divide each case by the actual data value so that we're scaling it, getting a fraction, and that allows us to compare between different data sets. If we look at data set 1, now we're taking the forecast minus actual, but we're dividing, in this case, by 177, so we get minus 0.292. That says that we underforecast by 29%. For the second data value, again because we're dividing by the actual value, we get 0.232, which says for that particular data value, we overforecast by 23%. We total up this first column. Second column is the same, except we get rid of the negative signs. We make everything positive by using the absolute value function, and we get a total for that column as well. Just like with the bias and the MAD, we divide by the 12 comparisons we have to get 0.037 for the mean percentage error and 0.148 for the mean absolute percentage error. This says that we overforecast by 3.7%. Here, our average error was 14.8%. For data set 2, the same process. When we look at the total, it's smaller, and we divide by 12 to get the average. we're over forecasting by 1%, and the average forecast is off by 6.6%, ignoring direction plus or minus. So comparing these two, for data set 2 on a percentage basis, on a relative basis, our mean percentage error is much lower, our mean absolute percentage error is much lower, so we are doing a better job forecasting. Again, the size of the errors is larger. This is obviously going to be a more important product, at least if the prices are comparable. We're selling many more units of this product, so it could be more of an impact being less accurate. But in terms of expecting accuracy out of a forecast, we're doing a much better job with dataset 2 than dataset 1. Looking back at our original data, we saw that we were doing pretty well, and then all of a sudden we weren't doing very well. If we're forecasting a large number of items, maybe a warehouse with 50,000 items, and we have an automated system, how do we tell the software to alert us to situations where we have this shift from doing well to not doing well? The tracking signal is a calculation that can be made that can tell you when you have a consistent problem with your forecast, a change in the bias in terms of now you're suddenly under forecasting as we are in this situation of over forecasting. That can be a signal for the forecaster to take a more in-depth look with that particular item. The tracking signal formula may look a little bit complicated, but it's fairly simple once we lay it out in a table. We're going to calculate the MAD at each period. So as we go forward, if we have 3 periods of data, we'll calculate the MAD for the 3 periods of data. As we get more data, we'll keep calculating the MAD for the data we have. And we're going to divide that into the running sum of forecast errors. Basically, the running total of forecast minus actual, ignoring the sign. The running sum of forecast errors is the difference between the forecast minus the actual, totaling that up for as much data as we have. And then we're going to compare it to a value of 4 or 5. So if the tracking signal is greater than 4 or 5, or less than -4 or -5, we're going to have a tracking signal value that suggests we should investigate what's occurring. Here's the tracking signal calculation for the data from the graph. We have 2 periods worth of data that we're using to initialize the model, so we do not want to calculate any error measures in the initialization period. This first column is forecast minus actual, just like before. So we have a forecast of 14.6, an actual of 11.4, and the difference is 3.2. The next difference is an under forecast of 2.9, an over forecast of 2.8, and so on. The running sum of forecast errors is just totaling this column up. So we just take 3.2, that's our value here. We take 3.2 plus 2.9, add those together, and the difference is 0.3. We add all 3 of these together and get 3.1. So 3.2 minus 2.9 plus 2.8 gives us 3.1. So this is basically a column that is totaling up the values in the previous column. Next, we take the absolute value of forecast minus actual. So we take this entire column, copy it over here, but we get rid of the negative values that we have. And we get a column with just the positive values of the difference between the forecast and the actual. The next column just totals it up. So we take 3.2 and move it over. We add these 2 together and move it together. We add these 3 numbers together, put it in the column. So it's a running total of the deviations that are absolute. Next, we calculate the MAD from this previous column. All we do is take this column and we'll divide by 1 to get 3.2. We'll divide by 2 to get 305. We'll divide by 3 to get 297, and so on. So we're calculating the MAD for however many comparisons that we have. The tracking signal is just the running sum of forecast errors divided by the MAD. So we have 3.2 divided by 3.20 gives us a tracking signal of 1. 0.3 divided by the MAD of 3.05 gives us 0.010. So in the beginning, when our running sum of forecast errors stays fairly small, may oscillate positive or negative, our tracking signal stays relatively small as well. But here, we start having a bias. We start under forecasting. So our running sum of forecast errors is getting larger and larger, getting more negative. And if we look at our tracking signal, it starts to grow more negative. And finally, here we're above a tracking signal of 4 in magnitude, here above 5. So some point between period 10 and 11, we would be notified that we see a trend in our data that indicates we may not have the right model for forecasting. If we look at this graphically, here's where the tracking signal is greater in magnitude than -4. Here's where it is -5.7. So somewhere at this point, depending on where we set our target at, we'd be notified that the tracking signal has gotten large enough that we need to investigate. And at this point, we may notice that we see a trend in our data. We need to change to a different model.